Question 1. Oliver records the distance from London to each of 8 cities in the USA. He also records the time taken to fly from London to each of these cities. The scatter graph shows this information, and part A says, by drawing a line of best fit, which I've done already, find an estimate for the time taken to fly from London to Chicago. And it says Chicago is 4,000 miles from London. So we read along from 4,000. You'd use a ruler in the exam. We'll read along to our line of best fit. Read downwards. And then read the scale really carefully. And I get something like, let's have a look, let's be careful. So that's 460, 470, 480, 490. So I'm going to say 490 minutes. The mark scheme allows from 480 to 500. It then says, why is your answer to part 1, I, only an estimate? Well, the line of best fit can vary, and the data is only like a sample, so the scale can't be read exactly. So that's the reason, and I'll write that down for you. And any of those reasons will be fine. So you can either say line of best fit can vary, or the data is only a sample, or the scale cannot be read exactly. Let's look at part B. It says, calculate the gradient of your line of best fit. Well, on the diagram, I've drawn a triangle, and this is 50 from there to there, but it's just a little bit more, so I said about 52. There would be 55, so there's about 52. It doesn't really matter as long as it's a little bit more than 50 and a bit less than 55, that's fine. And then you've got 500 here because I chose this point to be one part of my triangle because it intersected on 2 grey lines. So I did the distance and then divide that by the time. So we've got 500 divided by 52, and on the calculator, 500 divided by 52, that gives me 9.6 as the gradient, and that's to 1 decimal place. The mark scheme allows between 9.4 and 9.8, and of course if your line of best fit is slightly different, they'll allow for that as long as you've done a decent line of best fit. It then says, give an interpretation of the gradient of your line of best fit. Well, what will that be? Well, if you think about it, the gradient, we looked at the units here, so we'll look at the units. We had miles here, so I should do that as capital M really. So miles, and then here was minutes. So what would the gradient be? Well, yep, it would be miles per minute. So the gradient is miles per minute. And that would have to represent a speed, wouldn't it? A strange way of saying it. You'd be used to having something like kilometers per hour or miles per hour, but this is actually miles per minute, and it's a speed. Question 2. Part A says rotate shape S 90 degrees clockwise, center 5, 4, and label your image T. Well, I've done that for you, and if you wait for the rotation shape to start with S, it's coming up to it now. There we go, and then it's gone through 90 degrees, and now it is T. So you can have a look at that rotation there. All you've got to do is make sure you've got the vertices correct. So the vertices we had were 4, 5, and then 3, 7, and then 7, 7 for the triangle labelled T. So that's part A. And then it says, describe fully the single transformation that will map shape T onto shape S. Well, it's going to be the reverse of part A, isn't it? So what shall we say there? We shall say that it is a rotation, and it's going to be 90 degrees, but instead of clockwise, it's just going to be anti-clockwise about centre 5, 4. So nice easy marks there. Question 3. There's two rectangles shown and it says all measurements are in centimetres, and it says the area of rectangle A is equal to the area of rectangle B. Work out the perimeter of rectangle B. So the area of the first rectangle is just going to be 4x times 2.5, which is just going to be 10x centimetre squares. And the area of the second rectangle is just going to be 7 lots of 2x minus 3. So what we should do is just put these equal to each other. So we'd have 10x equals 7 lots of 2x minus 3. To give yourself a bit more room. And then we'd have 10x equals 14x minus 21. We will add 21 to both sides. And that will give us 21 plus 10x equals 14x. Take 10x from both sides, and that will give us 21 equals 4x. And then we can go from there. We can divide both sides by 4. So we'd have 21 quarters equals x. So it says work out the perimeter of rectangle B. Well, its perimeter is going to be 2 of those and then 2 of these. So when x is 21 over 4, that's going to give us 2 lots of 21 over 4 minus 3, which is 21 over 2 minus 3, which is 6 over 2. So that gives us 15 over 2. So the total perimeter for B is going to be 2 lots of 15 over 2 plus 2 lots of 7, which is going to be 15 plus 14, which is 29 centimetres. Question 4. The diagram shows a fair four-sided spinner, and Hasmeet is going to spin the spinner twice, and we've got to complete the tree diagram. So landing on A in the first spin, well, there's 3 out of 4 possibilities. And then again for the second spin, 3 out of 4. Landing on B on the first spin will be 1 in 4. And then landing on B again will be 1 in 4. And then this will be 3 in 4 and 1 in 4. First of all, we've got to now work out the probability that the spinner will land on A on the first spin and will land on B on the second spin. So our outcome is going to be 3 quarters times 1 quarter. And that's going to be 3 out of 16, so 3/16. Question 5. We're given the formula S equals pi squared lots of b squared minus a squared. And we're given that a is 8 and b is 10, and we've got to calculate the value of S. So we can do that on the calculator. So b squared, that's going to be 10 squared minus 8 squared. Now, you can either do the brackets first or you can put the whole thing in your calculator. It's really up to you. So let's try doing it the whole way first. So let's have a look. So pi first, so pi squared, and then we're opening a bracket, and then we've got 10 squared minus 8 squared, and then we're going to close the bracket, and that gives me 355.3057584, and to 3 significant figures, well, this 3 is not going to have any effect on this 5 here, so 355 to 3 significant figures. If you were less confident with that, you could go from here and say pi squared, and then do 10 squared on the calculator, and then 8 squared on the calculator, then work out the bracket, which is 36, and then on your calculator you probably do 36 times pi times pi. So we'll try that. So 36 times pi times pi, well, that's going to be exactly the same. So you don't have to do the whole thing on the calculator, you can do what you feel comfortable with. Question 6. Only blue vans and white vans are made in a factory. The ratio of the number of blue vans to the number of white vans is 4:3. Write down the fraction of vans that are blue. Well, we have 4 out of a total of 7 parts, so I'd go with 4/7 in this situation. For blue vans, the number of small vans to the number of large vans is in the ratio 3:5. Work out the fraction of the number of vans made in the factory that are blue and large. Well, if you look here, there are 5 out of a total of 8 parts that are large vans. But we're only talking blue vans here, because it says here for blue vans the number of small to large is 3:5. So that would mean that 5/8 of the fraction of blue vans will be large. So does anything cancel here? Yes. So we'd have 5/14 of the total number of vans are blue and large. Also, you may not have got 5/8 because you may not have cancelled down, so you may have got something like 20 over the original, which was 8 times 7, which is 56. So don't worry, you can leave it as 20 over 56 if you want. Question 7. Find the reciprocal of 5. Well, that's like doing 5 to the power -1, and that's going to be 1/5. Now that would be fine. If you said it as a decimal, then that would be 0.2. That's not particularly necessary. For part B, use your calculator to work out the cube root of everything under the root sign, which is 5 times tan 60 plus 1. Well, you can put the whole thing in your calculator if you want. So if you want to put it all into your calculator, then you want to open a bracket up, write 5 tan 60, making sure your calculator is in degrees, close the brackets, and do it to the power 1/3. One thing to say about doing the power on the calculator, some people have this button here, and when you do what's in here, just open a bracket and do 1 divided by 3. Okay, because if you don't, you might just do it to the power 1 and then divide the whole lot by 3, which is not what you want. So if you know the answer, just fast forward, that's fine. But I'm going to try and have a little look at what tan 60 is. So if tan 60 is root 3, so that's 5 root 3 plus 1 all to the power 1/3. So I'm going to try that, and there was no advantage to saying tan 60 is root 3, but again, it might cut down some worry for you if you actually do know some of the things that you're using. So 5 tan 60, or 5 root 3, plus 1. Now I'm going to actually press equals, and that's going to have in my calculator what the bracket is. I didn't do it all in one go. And now I'm going to raise that to the power, and that's 1 divided by 3. Now my calculator lets me do it without the bracket. You may have a calculator where you have this button on your calculator, and then if you're raising it to the power 1/3, then I strongly advise you opening brackets like that and closing them. So let's have a look. And I get 2.12975 4359. That's everything on my calculator display. If I want to try the whole thing, I'm going to give that a go and see if it's the same. Should be. So brackets 5 tan 60 plus 1, close brackets, to the power 1 divided by 3, and 2.129754359 is what's on my calculator display. Question 8. We have to make t the subject of this formula, where we've got p equals the square root of a plus t, or half of t. Now, I strongly advise squaring both sides to start with, so that would give us p squared equals a plus a half t, or t over 2. I then think it's a good idea maybe to double both sides. You don't have to, you can take a first if you want. So I'm going to times both sides by 2. I'll just write that down. So that will give us 2p squared equals a 2a plus t. See, even I nearly made a mistake there. So be careful, you're timesing both sides by 2. So this part has to be times by 2, as does this part. So that isolates the t here if I take 2a from both sides. So that's going to give me 2p squared minus 2a equals t. So I could take 2 out here as a factor and leave my answer as that. If we go back here to p squared equals a plus t over 2, well, you could take a from both sides instead. So that would give p squared minus a equals t over 2, and then times both sides by 2, and just leave it in the bracketed form instead of timesing the p squared and the minus a by 2, one at a time. And that would give you the same answer. Question 9. We've got to show that this angle here is 90 plus a half of x. And we've got to give a reason for each stage of our working. Well, the first thing to notice is that we've got an isosceles triangle EBF, and this is going to be x degrees because it's an alternate angle. So we would say that angle BEF equals x degrees because alternate angle to angle ABE, and you can write it like that if you want. So that's the first thing. The next thing we can think about is, well, if that triangle is isosceles, then we know angles in a triangle, so angles in triangle EBF equal 180 degrees, and we also know that base angles of this triangle are equal, and in brackets you can say isosceles. So this would have to be, there'd have to be a 90 in here and a 90 in here to make the 180, wouldn't it? But I know that if I've got a whole of an x here, I've got to somehow take that x away, because at the moment I've got 180 plus x, so these surely must be x over 2, mustn't they? Because they're the base angles and they're equal. So altogether I would then get 180, because the x here would cancel out with the minus a half x here and the other minus a half x here. So let's just see what we've got for w now. So if I create a little bit more room here, so we can also say that angles on a straight line add up to 180. So we know that 90 minus x over 2 plus w, I'm not being very good with my degree signs here, so I apologise for that. I'll probably miss them out somewhere else. is 180. So what we can do is we can take, let's see what we've got to prove first. We've got to say get W on its own. So we're going to have W on its own, so we're going to take 90 from both sides first. So let's do that. So take away 90 first. I'm dropping the degree sign for now. So we're going to have minus x over 2 plus w equals 90. And then we're just going to add x over 2 to both sides. So if we add x over 2 to both sides, that's going to give us here w equals 90 plus x over 2. So that wasn't too bad, as long as we've given our reasons. You can either keep the degree signs all in or go with what the question actually did, and that is leave them out. So that's that question done. Question 10. In 2016, the population of the UK was 6.5 times 10 to the power 7. Laura wants to calculate an estimate for the population of the UK in 2020. She assumes that the population increases by 0.6% each year. So using Laura's assumption, calculate an estimate for the population in 2020. So what we can do is, if we know that if we're in 2016, this is the population, then if we times by 1.006, that's like adding on 0.6% each year. So in 2017, the total population would be like so. And then if we times by 1.006 again, then we'd have the population in 2018, and so on. So the quickest way of doing it on the calculator would be to say times 1.006 to the power 4, because that would take us up to the year 2020, or 2020, whatever you prefer saying. So on the calculator, let's have a look what that gives us. So we've got 6.5 times 10 to the power 7 times 1.006 to the power 4. So on the calculator I had the following. We only want an estimate, so I'm going to leave it in standard form. So 1, 2, 3, 4, 5, 6, 7. So that will be 6 point, and I'm going to round this to two significant figures. 6.7 times 10 to the power, well, we went 1, 2, 3, 4, 5, 6, 7. I'm going to put that to two significant figures. Let's have a look at the next part. Kieran also assumes that the population of the UK increases by 0.6% each year. He says that it will take over 80 years for the population to increase by 50%, because he quotes this calculation. Well, he's kind of looked at 50% and he's divided it by how many 0.6% go in. And because he got 83.3 recurring, that's more than 80, hence he validates his position. But he uses a simple increase, whereas it is a compound growth. And you can put in brackets changes every year. So just think about the first part. You had the initial amount, and then you increased it by 0.6%, and then so that changed over the first year, but then you were increasing by 0.6% again, but not to this original amount each time. You were doing it to a differing amount every year. So that's why it's compound, and his calculation is based on a simple, literally a simple method of increase. assuming that the population of the UK increases by 0.6% each year, show that the population of the UK each year forms a geometric progression. Well, all a geometric progression is something where you always multiply successive terms by the same number. For example, if we had the initial population in year 1, in year 2 we'd have that population times 1.006. In year 3 it would be p times 1.006 squared, and then by the time we get to the nth year it would be p times 1.006 to the n minus 1, because it's always one less for the term number. And here you can even say that is 1.006 to the power 0 if you want. That comes up at A2 and A level quite a lot. So my advice is all you have to say is that it always increases by the same amount each year, and any convincing conclusion, i.e. the terms are generated by multiplying previous terms by 1.006 every time, so a geometric progression is formed, that will be fine. By the way, this number here, the number you keep timesing by each time, is called a common ratio. And it's called a common ratio because if you have the first term here, say A, and then your second term, and then your third term, if you divide one term by the one before, you'll always get R. So if you divided this one by this one, you'd get R again. So all the successive terms divided by the one before always give something called the common ratio. Question 11. Anna and Bill share some money in the ratio 2 to 5. So let's call that money X, an amount X. So Anna would get 2 out of a total of 7 parts, and Bill would get 5 out of 7 parts. Now, that would mean Anna would get 2/7 of the total amount of money, and Bill would get 5/7 of the total amount of money. So that's Anna and Bill sorted out. Carl and Donna share twice as much money, so they're not looking at X now, they're looking at twice X, whatever X is. And they share the money in the ratio 3 to 1. So Carl would get 3 out of 4 parts, but not of X, 2X. And Donna would get 1/4 of the same amount. So if we just write these down as simply as possible to start with, we'd have for Anna 2x over 7, Bill 5x over 7, then we'd have Carl, I can cancel this down here, to 3 over 2x, so 3x over 2, and Donna, 2 divided by 4 is a half, so just x over 2. So what I can now do is, I can divide all of it through by x, because they have x in common. This here would be then 1. And so I'd have 2/7, 5/7, 3/2, 1/2. But if I want to get rid of the fraction parts, it's not the fraction parts, the denominators rather, and the denominators are 7ths and halves, if I multiply by the lowest common multiple of 7 and 2, which is 14, then I think you can see very quickly 7s into 14 is 2, and 2 times 2 is 4. 7s into 14 is 2, 2 times 5 is 10. 2s into 14 is 7, 7 3s are 21. And 2s into 14 is just 7 times 1 is still 7. So the answer of A to B to C to D as a ratio would be 4 to 10 to 21 to 7. Question 12. So we've got a right-angled triangle, PQR, and it says the length of QR, so we know that QR is 60%, so 0.6 of the length of PR. So why don't we just call PR something like X, and then QR must be 60% of that. So 0.6 is like 3/5, so we can either just call it 0.6 or 3/5 if you want. So that's going to be 0.6x. Now we want the sine of QPR, so this is the angle here, theta, and sine is opposite over hypotenuse, isn't it? So we're going to have to find the hypotenuse here, which is fine, we can use Pythagoras. Now obviously you can use your calculator here, it's probably better. So we know that we're going to have x squared plus 0.6 squared, so that's going to be 0.36, isn't it? So that's going to be 0.36 x squared, and you can just check that on your calculator. So 0.6 squared is 0.36, and then we're going to have to square root that at the end. So what we've got here is, and this is where you might get a bit confused, so let's just write this out slowly. If I've got x squared plus 0.36 x squared, then what I really have is 1 plus 0.36, which is 1.36 x squared. And if I square root that, that's going to give me an x and then the root of 1.36 in here, which I'm not bothered about too much at the moment. So let me put these in. So let's put this in. So we've got x root 1.36. So the sine of theta, which is the same as the sine of QPR, well, that's going to be the opposite. So let's go through that. That's the opposite here, which is 0.6x over the hypotenuse, which is x lots of 1.36. Luckily, the x's cancel, so all we've got is 0.6 over the root of 1.36. It wants it to 3 significant figures, and it only wants the sine of QPR, so we haven't got to actually find the angle, we just got to find the sine of the angle. So we're going to do 0.6 divided by, and then the root sine, 1.36, press equals there, and it gives me here, and I'm going to write this on all the numbers on my calculator, 51449575554, and I want that to 3 significant figures. So this 4 is going to have no effect on here. So 0.514 to 3 SF, 3 significant figures. Question 13. It says there are 5 graphs and each graph shows either direct proportion or inverse proportion. And we've got to match these up with the equations that are given in this grid. So I think the nicest one by far is this one. It's a nice linear. So y would be, so I'm going to go with B, saying that y would be proportional to x because it's a straight line. So y would be equal to kx for some k. So that's going to be this one here. So let's get rid of that one. Now this one here is one that you may have been aware of, and that is as x increases, y decreases, and as x decreases between, say, 1 and 0, y increases. And that's where we have a situation where y is inversely proportional to just x on its own, so y would be equal to k over x for some k. So that's going to be this one. Now this one looks very much like the quadratic case, doesn't it? So, well, that's in here. So y is equal to kx squared. That's going to be this one. That's D. So we've got to be careful here. This one seems to show that when x gets large, y seems to, well, how can I put it? It doesn't get massively large, does it? It doesn't do something like this, where it gets exponentially large. It kind of peters off a little bit. So let's have a think. If it was this one and it's got really large, wouldn't that have more of a shape like this, where it was growing really fast? And what I'm saying to you is here, you can then deduce which one you're looking at. So E must be this one, and C must be this one. So if you just kind of think about the shape of the graph, then and when x gets large, what happens to y, and you can kind of think about that in your head, you can deduce which ones are which. So that's the table complete. Question 14. A cafe owner sells 10 different types of sandwich. Raheem buys a different type of sandwich on Monday, Tuesday, and on Wednesday. So a different type. In how many ways can he do this? Well, there would be 10 ways of choosing the first type of sandwich, wouldn't there? And then once you'd chosen one of those, there'd only be 9 ways for the Tuesday's sandwich, and then as you've already chosen to make it different, you'd only have 8 choices for the third. Now, if you did this as some kind of outcome tree, you'd have 10 branches for the first, and for each of those 10 you'd have 9 for the second, and for each of those 9 you'd have 8 for the third. So it's exactly what we do with a probability tree. We would multiply all of these outcomes. So you can try drawing the whole thing if you want, but you're going to have 10 times 9 times 8 branches on the very last part of the tree, and 10 times 9 times 8 on the calculator would be a total of 720 ways. Question 15. The table shows some information about the times a group of students took to do a park run. I think the first thing we've got to do here, if we want to do a histogram, because it says draw a histogram for this information, is find the frequency density. Now, what does that mean? I always look at a histogram as being the area of each bar represents the frequency. So in the first one, I'll just explain the first and the second one, then we can just quickly do the rest. You kind of want it going from 0 to 25 on the t-axis. So for example, you want it to be from here to 25 mark. So it's kind of having that length of 25, but because the area is 20, which is the frequency, you've got to multiply it by something to give that area of 20, and that's how high it's going to be. So the calculation you would do on your calculator is 20 divided by the class interval, which is 25, which is 0.8. So on your table here, you can just write FD for frequency density, put the calculation, if that's all right, if you want to do that, and then you can just write in brackets 0.8. So what will the next one be? We want to get an area of 35 for the bar, and we've got an interval here of 20, so we want to do 35 divided by 20. And on the calculator, 35 divided by 20, that gives me 1.75. So I finished off the rest for you, and all we have to do now is do a scale on the frequency density axis. So it looks as though we want to go as high as 5.8. So let's have a look. So if we do our scale going 1, 2, 3, 4, 5, 6. The first one is as high as, it was 0.8, wasn't it? So we want to go 0.5, 0.6, 0.7, 0.8, and that's to there, and then do that in blue. And there we have the first bar. The second one was as high as 1.75, and the interval width was 20. So it went up to, once you're in the first one, it's easy, just keep going to the end point. So you want to go as far as 45 and as high as 1.75. So 45 as high as 1.75. So there's 1.5, 1.75 is halfway there, and so we can do that one like so. I'm just going to do this one, then I'm going to finish the rest off. Apologise for my bad lines, they're not very good. And there's our second one, and I can just finish the rest off now. So I finished that off the best I can. If you find any errors, then please let me know, do comment, but that's my finished histogram. Right, let's move on. Question 16. How can we show that this equation has a solution between x equals 2 and x equals 3? Well, if we put x equals 2 into the equation, what do we get? We'd get 8 minus 3 lots of 4 plus 3, which is 8 minus 12 plus 3, which is negative 1. Okay, so that's negative. I can put a minus sign with VE afterwards to be short for negative. If I then put 3 in the same expression, I'd have 27 minus 3 times 9 plus 3, which is 27 minus 27 plus 3, which gives you 3, which is positive. So what you've got is a change of sign, and what that basically means is that when you've got a solution point here, x equals 2, not a solution point rather, a value x equals 2 and a value x equals 3 on the x-axis, it means that what we had here was a situation where the curve did this. So at this point 2 it was 1 below the axis, and at the point 3 it was 3 above. That's all that is saying. So basically there must have been a root somewhere between, or a solution somewhere between x equals 2 and x equals 3. So you're always looking for a change of sign. So the best thing to say is change of sign. Let's write that properly. Therefore, solution lies in the interval, and you can write the interval like 2, 3. It's kind of like a coordinate, but it stands for the interval where it can't be 2, can't be 3, but somewhere in between. So let's look at the next part. Show that the equation x cubed minus 3x squared plus 3 equals 0 can be rearranged to give this. Well, one neat way of doing it in the exam, which is a bit of a shortcut, is to write the answer at the end, and then you can undo it. So you can cube both sides, and then you can take 3x squared from both sides, add 3 to both sides, and then you're left with where you started. If you don't like that, you think that's too bad, then, well, you can do it whichever way you want, but when you've written your final answer, there'll be no necessarily way of telling how you got there. But it's not a bad idea to go from what you've got to show to work backwards. It's quite a good practice to do that. So try it backwards and forwards, and you can decide when you get into the exam which way you're going to do it. So part C, it says starting with our first initial value to be 2, use the iteration formula, and it has the new term we want is found by substituting into this expression, which is a rearrangement of the initial cubic we want to find solutions with. I won't go into all the details right now, but basically we want to find the value of x subscript 2. So we've got to use our first value, so there's subscript n there, forgot to write that. So when we have here our first initial value of 2, that's when n is 0. So x 1, that would just be 1, would be 3 lots of x0 subscript 0 squared, which is 2 squared, minus 3, which gives us the cube root of 3 times 4 minus 3, which is the cube root of, well, that's 12 minus 3, which is 9, the cube root of 9. And you can do that on your calculator. 9 to the power, and I do brackets 1 divided by 3, and I get 2.080083823. And then I can put this value on my calculator into the formula, into the iteration formula here again, and get the next value. There is a quicker way. You can just type in 2 on your calculator. So 2, press enter, and then that's the answer stored into your calculator. And then all you need to type in is 3 lots of ans squared minus 3 to the power 1/3. So I'm going to do that now. Brackets 3 ans to the power 2, so squared, minus 3, close brackets, to the power, and then I'm going to put brackets around here so there's no confusion. 1 divided by 3, close brackets, press enter, and I'll get this value here. And all I've got to do is press enter again, because it then uses that value and it puts it back into here automatically. And so I would get, so this would be x1, so x2 would be 2.153015141. It wants it to 3 decimal places. So I would say x2 is 2.153 to 3 dp. Question 17. A factory makes ice cream tubs in 2 sizes, small and large. Well, we're given the fact that they're similar to each other. Now we have the length here of the small one, and what we can say is that the length here is 5 centimeters. So if we want to work out the scale factor of enlargement here, if we knew something about the length here, say that was 10, then we'd know the scale factor of enlargement for length was 2. So the area scale factor would be 2 squared, because it's 2 in both directions, and the volume would be 2 cubed. But in this situation, we don't have a length scale factor for this one. What we are told, though, is that the volume of the small tub is 150 centimeter cubes, and the volume of the large tub is 500 centimeter cubes. So that's good. So we actually have not a length, not an area, but a volume relationship. So to get from the smallest volume, what do we have to times by to get the largest volume? Well, if we divide both sides of this by 150, we get 500 divided by 150 is our volume scale factor. So let's do that on the calculator. 500 divided by 150. Well, that gives me 3 1/3. So 3 1/3 is going to be 10/3. So I'd like to keep it as a nice fraction like that. So think, if we knew the area one, wouldn't we square that to get the area? And then wouldn't we cube the length one to get the volume? So if we want to go from volume back down to length, we'd have to cube root 10/3. So our length scale factor is the cube root of 10/3. And I don't know what you're most comfortable with. Personally, I'm more comfortable with 10/3 to the power 1/3. Be careful when you do that on the calculator. Put a bracket here. So I'm going to say bracket 10 divided by 3, close bracket, to the power bracket 1 divided by 3, close bracket. So my length scale factor is 1.493801,582. So all I have to do is times 5 by that number, and I will get the height of the large one. So times by 5, and I get 7.46900791. But it wants it to 3 significant figures. So the 9 does change this 6 to a 7. So my final answer would be 7.47 centimetres to 3 significant figures. Question 18. We have x minus 8, lots of x plus 4, and that's equal to x minus a all squared plus b for all values of x. We've just got to find the values of a and b. Well, there are a few ways of looking at this. One way is to expand this, so we'd have x squared, and then we'd have 4x minus 8x, that's minus 4x minus 32. And then let's work on that. We can complete the square. So that would give us x minus 2 all squared minus 4, and then the minus 32 is left, which gives us x minus 2 all squared minus 36. So it looks as though a is going to be 2 and b is going to be negative 36. Another way of looking at this question is to say, well, it cuts here at x equals 8 and it cuts here at x is negative 4. The line of symmetry on this quadratic is always the mean of the solutions. That's always the case. So the mean of 8 and negative 4, well, 8 and negative 4 is 4, halved is 2, and this is why you can always see that there's a link in the completed the square form. So you could deduce 2 from there directly. Let's move on to the next question. Question 19. The diagram shows a sector of a circle of radius 9 centimetres. The sector has a perimeter that's all the way round is 25 centimetres. So we can realise that this is going to be 7 centimetres, isn't it? We want to work out the value of x, and that's in degrees. So we've got to give our answer correct to 1 decimal place. Well, if we knew the whole way round, then that would be pi times the diameter. So the circumference would be pi times the diameter, which is 18 in this case. But we only have 7 centimetres for this part, this minor arc here. So if we work out what fraction this part of the circumference is compared to the whole circumference, we can work out what fraction this is of 360, because don't forget, all the way round is 360. So 7 divided by pi times 18, which you can write as 7 over 18 pi. That's got to be in the same ratio as x is to 360. So think about it. X, the angle, told us what fraction 7 centimetres is out of the entire circumference, which we can work out. We know that an entire revolution is 360 degrees, so x, i.e. the angle, the amount that x over 360 is worth has to be in proportion to 7 over 18 pi. So what we can do is directly solve this equation here for x, and you can see that all I have to do is times both sides by 360 here. And that's going to give us x equals 7 times 360, all divided by, that's important, 18 pi. So let's do that on the calculator, and to be safe, I'm going to put a bracket up here, and I'm going to put a bracket underneath here. So bracket 7 times 360, close bracket, divided by open bracket 18 times pi, close bracket. So I have x is 44.56338407. We want it to one decimal place. So the 6 would change as 5 to a 6. So we have 44.6 degrees to one decimal place. Question 20. M equals 1 over P times S. P is 5.37, correct to two decimal places. So the way I do this is that I say to myself, in this particular place value, we're looking at not tenths but hundredths. So I take 1/100th and I halve it, and I add 0.005 to 5.37, and I take 0.005 from 5.37 to get the upper and lower bound. So we would have the upper bound to be 5.375. Some people like to use 5.3749 recurring and write that down, that's fine. Or as low as 5.365. S is 2.9, correct to one decimal place. So the one decimal place value is 1/10. I write a 0 at the end because it's easier to see how to halve it. So again, I add and take 0.05. So my upper bound would be 2.95 and my lower bound would be 2.85. So we want to calculate the upper bound, the most, for the value of M. Well, if we want the most, then we want the product PS, P times S, to be the least, because 1 divided by the least will work out to be the most. And I think about cakes and people. If you want the most cake, you want the cake to be the most and you want the people to be the least. If the amount of cake was fixed and you wanted more, you would have less people show up, because then there'll be more cake per person. So we want this product to be the lowest. So to get the lowest product, well, I think we'd want P to be the lowest and S to be the lowest. So the upper bound for M would be 1 over the lowest for P, which is 5.365, multiplied by the lowest for S, 2.85. So I'm going to put that into my calculator. So I've got 1 divided by bracket 5.365 times 2.85 close bracket. And that gives me 0.065401153. Question 21. The diagram shows an acute angle triangle ABC, and we've got to prove the area of that triangle is a half AB sine C. Well, a nice way of doing this, which you've probably been shown by your teacher many times, is to drop a perpendicular here. Let's call this X, and let's call the perpendicular H. Now, we know if we want to use the angle B here, say, we'll call this B hat, and this angle here C hat, then we know in this right angle triangle that the sine of B equals the opposite to that, which is H, over the hypotenuse. So we get H equals C sine B. In the second triangle, we can say that the sine of C is the opposite to that c, which is h, over the hypotenuse in this case, which is b. So we get h is b sine c. Now, when we're looking at the area of this triangle, the area of this triangle is the height times the base halved. So we've got a few different options here, but we want the option involving the a and the b. So we're not going to look at this option because it involves the c here. So all we've got to say is the area is equal to h, which in this case is b sine c, times a halved. And that's exactly the same as just writing ab sine c, half of it. Okay, so maybe a slightly clumsy way of doing it here. I think I prefer ab sine c over 2 from where I've been here, but a half ab sine c is probably how people remember it the most when saying it. So there you go. So there's two options there. Of course, you could have involved the triangle, the vertex A by twisting the triangle round, so B would be the base, but then you would not incorporate AB with the angle being C. So when looking at this question and proving something, it's probably best to look at the angle you want first, and that will tell you which right angle triangle to be in. Question 22. A solid cuboid has a volume of 40 centimetre cubes. The cuboid has a total surface area of 100 centimetre squares, and one edge is given as 2 centimetres. We've got to find the length of a diagonal. Right, a diagonal of the cuboid. So let's build a bigger model of this. Doesn't matter if it's to scale or not. And you can do this in the exam, it will help. Now I believe a diagonal to be, say, from one corner going right through the cube to another edge. So for example, it would be this dotted length here. So we're given that one of the lengths is 2 centimetres, so we'll call the other ones here x and y. Okay. Luckily we're given the volume, so we know that 2 times x times y is 40. So that means xy must be 20, so that's important. And we also know that the surface area is 100. So how do we get the surface area? Well, we can do 2 of these faces here. Okay, first. So that will be 2x, 2 times x for one of them, and then doubled because there's 2 of those faces. Plus, we can then do 2 of these. So that will be y times x, won't it? Because that's x as well. So x times y, but doubled because you've got 1 on the back as well. So that shouldn't be too difficult to write down algebraically. So we're going to have x times y, but 2 of those. And then lastly, we're going to have 2 of the top parts. And they're going to measure 2 by y. So we're going to have 2 lots of y, but we've got 2 of those because we've got 1 on the bottom as well, don't forget. So we know that 4x, that's this part, plus 2xy plus 4y has got to be 100 because that was the surface area. So that's another nice formula that we can use. So what we can do is we can work out x and y now because we've got 2 equations in x and y. So that's really handy for us. So we've got xy is 20, and we've got 4x plus 2xy plus 4y is 100. So I think with the second one I'm going to halve everything because I can see everything has got nice even multiples. So I can halve this number, I can halve that one, and halve that one and get 50. So I've got this one and this one. So I think the first thing I'm going to do is I'm going to say let y equal 20 over x from this one. So I've got 2x plus xy. I'm going to be crafty and put a 20 there because that's what xy is. Plus 2y, so that's 2 times y, which is 20 over x, equals 50. So what I will have then is 2x plus 20 plus 40 over x equals 50. So I can take 20 off both sides, multiply everything through by x. So I've got 2x squared plus 40 equals 30x. I can halve everything because they're nice even multiples. So I get x squared plus 20 equals 15x. And that's exactly the same as saying x squared, I can take 15x off both sides, plus 20 equals 0. Now looking at that equation there, it doesn't look like it's going to factorise because I can't find factors of 20 that give negative 15. So I'm going to use the formula. So x is going to be minus b plus or minus the square root of b squared, which is 225, you can use your calculator for that, minus 4 times a times c, all over 2a. And don't forget here, a is 1, b is negative 15, and c is 20. So x would then be 15 plus or minus, and we've got 225 minus 80. Sorry for the print underneath, I hope you can see it okay. And then neatening that up, we've got 15 plus or minus, and that will be 145 square rooted over 2. Now, the interesting thing about this then is we've got two possibilities for x, because don't forget I could have had the x here or I could have had the x here and that could have been y. Okay, it was arbitrary which way I put the x down. So one x value, and I'll use my calculator, so we'll have 15 plus the square root of 145 and then divide that by 2, and that gives me 13.52079,729. Or I can do 15 minus, so I can have 15 minus the square root of 145, divide that by 2, the whole thing by 2, and that gives me x could be 1.479202711. So I can be clever here. I can say, well, I found x and I found y. Now the reason for that is because, don't forget, I could have put, and I'll just enlarge this a little bit. What I could have done is I could have labelled this one as x, which I did originally, and this one as y, or I could have labelled this one as x and this one as y. If you don't like the idea of that, thinking that you've already got x and y just because you've got two values of x, then you can go back to this formula here, y equals 20 over x, plug in one of your values, for x, and you'll have 20 divided by, say, which one should we use? 13.520797929, and you will get 1.479202711. And if you do 20 divided by 1.479, you're going to get 13.520, and so on. So they're the values found. So I think we've got to come back to the diagram now and see whether we can find this diagonal. Well, for me, I'm going to use this black pen here, and I'm going to just increase the pen size here. What I'm going to do is I'm just going to outline a nice right-angled triangle here, and I know that this is a right angle here because this is a vertical height and the other length here is on the horizontal. It's flat on the table. Now, some of you might find it difficult to work out what this diagonal is here, so I think you can fast forward this part by pressing the right key on your keypad or press the screen on your device if you want to fast forward, but I think some of you might benefit from knowing how to find the diagonal of a cuboid generally, and then we can just put the numbers in, can't we? So if you have a cuboid like so, won't take too long to do. If you want to find the diagonal, one of the best ways of doing it is you use Pythagoras twice. So we'll mark in the diagonal we want to find. It was this one here, and we're just going to put in a nice right-angled triangle to help us. So don't forget we want this length here. So we've already got this one, that's fine. We can just call that A. We've got that. Have we got anything else? Well, unfortunately, we only have B and C. We've already worked out what those lengths are. So here's the clever thing. We can use Pythagoras to get this length here, because that length is, and we'll call it D, is B squared plus C squared square rooted, isn't it? That's what D is. But now we can find the missing length, and we'll call that X, because if we use Pythagoras again, i.e. we want to find X, so X squared, and don't forget it's in a right angle triangle, so we can use Pythagoras. X squared is going to be A squared plus D squared. But what was D squared? D squared was B squared plus C squared. And so D squared is going to be all of this squared, which is nicely just B squared plus C squared, because we unlock the root sign by squaring. So if we square a root sign, we're just going to get back to what we have inside here. So X squared is actually going to be A squared plus B squared plus C squared. Now, that's really nice because that was just the lengths of our original cuboid, wasn't it? So X has got to be the square root of all of that. So now we're ready. We can just put the numbers into our calculator and go from there. So I think we've got all the numbers we need. Don't forget we were given one of the lengths of the cuboid, weren't we? So our missing length, our diagonal, should be 2 squared plus, let's do this one first, 1.479, I'll do dot 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 because I haven't got room to do all of it, squared plus 13.520 dot dot dot, and all of that squared. So let's put that in the calculator. Well, what I get is a nice number under the root sign. So the square root of 189, which is 13.74772709. centimetres. So let's just check the accuracy that it wanted it to. It wanted it to 3 significant figures I can see here. So 1, 2, 3. The 4 doesn't change the 7. So we're going to say 13.7 centimetres to 3 significant figures.